Hello everyone, here's our chapter 2. Okay, alright. So, what are we going to do in chapter 2? So, we're going to learn about the components of matter. In here, we're going to learn about elements, compounds, and mixtures, atomic overview, observations that led to an atomic view of matter, Dalton's atomic theory, observations that led to the nuclear atom model, and the atomic theory today. Okay, also we're going to look at the elements. Where do we find the elements? We find the elements in the periodic table. Okay, and also going to learn about bonding, how the atoms are bonded, how the compounds have been formed. Okay, also we're going to learn about how to name the formulas, and if the name is given, how to write the formula, and then how do you find the mass of a compound, and then mixtures and classification and separation of mixtures. So what is an element? Element is the simplest type of substance with unique physical and chemical properties. Element consists of only one type of atom. It cannot be broken down into any simpler substances by physical or chemical means. Can you give me an example of an element? Where do we find elements? We find elements in the periodic table. So, can you tell me name of an element? Where did you say? Sodium? Okay, yeah, so sodium is an element. Very good. And what about sulfur? Sulfur is an element too, right? So these are all the elements where we find in the periodic table. And then you can also have carbon. Yes, carbon is an element too. And what else? Potassium. So basically, elements are found in the periodic table. Okay, and then we have molecules, a structure that consists of two or more atoms that are chemically bound together and thus behaves as an independent unit. We call them as molecule. Can you give me an example of a molecule? You can find a molecule. There are two or more atoms are chemically bound together. What did you say? Oxygen? Yes, oxygen is a molecule, a diatomic molecule. A hydrogen is a molecule too. And water, H2O, is a molecule. And then nitrogen. So all of these are molecules. Okay. And there are 7 diatomic molecules. That is how you find in the nature. Like for example, oxygen, hydrogen, nitrogen, fluorine, chlorine, bromine, iodine. Those are the 7 diatomic molecules that you find in nature as diatomic molecules, not by singular element. Okay. And then the next one is a compound. Compound is a substance composed of 2 or more elements that are chemically combined. Okay, so that is a compound. So what you're seeing here is the molecules of a compound. It could be carbon dioxide is a compound, CO2, and a water can also be a compound. And then we have mixture. A mixture is a group of 2 or more elements and or compounds that are physically intermingled. So in a mixture you will find elements, you can find molecules, you can find compounds. So we find everything in a compound. Not compound, mixture, sorry. Some properties of sodium chlorine and sodium chloride. Now sodium is an element and chlorine is a molecule. That's how we find it in the nature. And sodium chloride is a compound. Now here you can see some properties of sodium. Sodium is a solid and it is very reactive. You put a piece of sodium into water, explosion, because it generates hydrogen gas. Okay, so we have to handle it very care. You can see the person is wearing gloves also. Sodium. Okay, and this is chlorine. Chlorine is a gas and that is also a toxic gas. Okay, and it's a yellow green gas. behavior in water. Sodium reacts and chlorine dissolves slightly. So sodium is a pretty dangerous metal, and then the chlorine is also not that friendly. It is also a hazardous gas. Okay, and then you put sodium and chlorine together, you form sodium chloride. Are you guys familiar with sodium chloride? Where do we find sodium chloride? On your table. That's your table salt. Remember, we cannot eat, we cannot cook without salt. Salt, sodium chloride adds a beautiful or the yummy taste, right? If you have a pinch of salt, it brings out the taste of the other food ingredients too. But it is a very friendly, we can eat, we can consume, right? We enjoy it. But if you look at the elements that it formed, sodium and chlorine, they are separately, they are not that friendly. But once the compound is being formed, it becomes a different compound. It has different characteristics. Okay. So sodium chloride is a salt, table salt. That's how we know about it. But as we learn this chemistry course, you will see there are many other salts available for us, not just only sodium chloride. Okay. Following scene represent atomic scale view of 3 samples of matter. Describe each as an element, compound, or a mixture. So this first one is a mixture. You can see molecules, right? 2 different types of molecules. You can see a compound, so obviously this is a mixture. And what about B? What do you think B is? Element. Very good. It's an element. B, and C is a compound. Okay, so that's easy. It's not that bad. Okay, so now we're going to learn about some laws in chemistry. So the first law that we're going to learn is the law of mass conservation. What does that say? It says the total mass of substances does not change during a chemical reaction. Okay, so here what you are seeing in the left side is the reactants before the reaction begins. You have lead nitrate solution and a sodium chromate solution, and this is the mass before the reaction. So your reactants are in this glassware, in the Erlenmeyer flask and in the graduated cylinder. You put them together, you mix them together. You put what you have inside the graduated cylinder, which is sodium chromate, into lead nitrate solution. Now you have a yellow color solution. Once it's been mixed, you form solid lead chromate in sodium nitrate solution. And then you're going to get the mass of the product along with the glassware. You can see the mass is same as the mass before. So mass before the reaction equals the mass after the reaction. So that is the law of mass conservation. Total mass of substances does not change during a chemical reaction. Okay. And little bit in more detail about the law of mass conservation. The total mass of substances present does not change during a chemical reaction. Let's say that we are going to do a reaction, calcium oxide with carbon dioxide. When you put these two together, it forms calcium carbonate. Okay, so calcium oxide is this one, carbon dioxide is this one, and it's going to form calcium carbonate. If you look at the mass of the reactants, calcium oxide 56.08, carbon dioxide 44, and calcium carbonate is 100.08. Now you may be wondering, how do we get these masses? Basically, these masses come from your periodic table. This is if you take 1 mole of calcium oxide, what is the mass? Now, all of you guys can have your periodic table handy when you are studying these lectures. Now, if you look at your periodic table, the mass of calcium is 40. Okay, 40 grams. And then if you look at oxygen, mass of oxygen is 16 molar mass. 15.99, I'm going to round it up to 16. So 40 plus 16 is 56. I'm going to see if I can find a periodic table so I can see the decimals. I just wrote this down what I remembered, but anyways, 40.00 maybe. Okay, wait a minute. .08. So calcium is 40.08. And you get these numbers from your periodic table. 40.08, oxygen 15.99, or you can say 16.00. So together calcium oxide is 56.08. And carbon dioxide, carbon molar mass is 12. And oxygen molar mass is 16, and there are two oxygens. So 16 times 2 is 32. 32 plus 12 is 44. That's how you get the number here. And then to find out the calcium carbonate, calcium molar mass is 40.08 and carbon is 12. You get these numbers from your periodic table, and there are three oxygens. Each oxygen is 16. 16 times 3, 48. When you add up all this, that's 100.08. Okay, so you can see here mass of the reactant 16 plus 32 plus 12, 56 plus 44 equals 100.08. That's the mass of the reactants, and then the mass of the products also 100.08. So the mass of the reactants are equal to the mass of the products. So that is the law of mass conservation. And then the second law is law of definite or constant composition. What that means is no matter what the source of a compound, let's say you have calcium carbonate. So this statue is made up of calcium carbonate. And these coral reefs are also made up of calcium carbonate. No matter what the source of the compound, in this case calcium carbonate, always 40 mass percent would be calcium, 12 mass percent would be carbon, 48 mass percent would be oxygen. Remember, we talked about earlier that the calcium molar mass is 40 and carbon is 12. Oxygen 16 times 3, 48. When you add up all these, that's 100.08. Okay, 100.08. And if you want to find out what is the percentage of these, like if you take 40, the 40 grams of calcium would be in 100 grams of calcium carbonate. Okay, so 40 grams of calcium is in 100 gram of calcium carbonate. And if you want to find out the percentage, you multiply it by 100. So that will give you 40% of calcium. That's how you find out the percentage. And similarly, if you want to find out the percentage of carbon, 1 mole of carbon is 12 grams. And then molar mass of calcium carbonate is 100 grams. And this is for carbon. And you multiply it by 100. That will give you mass percent of carbon. Similarly, oxygen would be 48 mass percent. So since calcium carbonate composition doesn't change, always these percentages would remain no matter what is the amount of sample you are taking. Okay, so it's continuing with the calcium carbonate example. If you have a 20 gram of sample, how do you find the amount of mass of calcium? carbon and oxygen. So if you have 20 gram sample, analysis by mass of grams per 20 grams. Now let's say if you start with the 20 grams, you want to find out how much calcium in it, in a 20 gram sample. So you want to find out in a 20 gram of calcium carbonate, but we know the ratio. If you take 100 grams of calcium carbonate, 40 grams would be calcium. So 2 times 4, 8 grams. So that's how you get this 8 grams if you have a 20 gram sample. Also, if you have a 20 gram sample of calcium carbonate, what's the amount of carbon? There would be molar mass of carbon is 12 grams. 12 gram is in 100 gram sample because the molar mass of calcium carbonate is 100. And then we were looking at 20 gram sample. Okay. I forgot to write the 20 gram to begin with. Let me do that again. So you're starting with 20 grams. So if you take 20 gram sample, your ratio is 100 gram calcium carbonate. You have 12 gram carbon, and 12 is the molar mass of carbon, 100 is the molar mass of calcium carbonate. So this 0 can get cancelled. 24 over 10, that is 2.4 grams carbon. Always you know the ratio. If you take 100 grams, that's 40 gram of calcium. You take 100 gram of calcium carbonate, carbon would be 12 grams. So you can find out the ratio. Okay? And same for the oxygen. So if you have a 20 gram of a sample, what's the amount of oxygen? So in a 20 gram, we know the ratio for 100 gram calcium carbonate, there are 3 oxygens. So each oxygen is 16. So 3 times 16 is 48. 48 times 2 is 96. 96 over 100 is 9.6 grams oxygen. So that's that 9.6. And this is for the carbon. Okay. Similarly, if you are looking at 1 part by mass, this would be the mass fraction. 0.4 calcium, 0.12 carbon, 0.48 oxygen. Okay. And then if you want to find out by percentage, so these are the percentages: 40%, 12%, 48% in 100% by mass. Okay, analysis of 84.2 gram of uranium containing compound pitch blend shows it is composed of 71.4 gram of uranium with oxygen as the only other element. How many grams of uranium can be obtained from 102 kilogram of pitch blend? Okay. So it is asking, if you have 102 kilogram of pitch blend, how many grams of uranium are there? Now we can use the same ratio that we were working on this problem here, or the concept. So here we have, if you take 84.2 grams of uranium containing compound, 71.4 gram of uranium are there. Right? It doesn't matter where you find the pitch blend, that ratio will remain the same. Meaning 71.4 gram of uranium in 84.2 grams of pitch blend. Just like if you had 100 grams of calcium carbonate, the amount of calcium would be 40. So likewise, you had the same ratio. Now it's asking if you had 102 kilograms. What's the amount of uranium? So basically you write 102 kilogram and you use the ratio 84.2 gram pitch blend. You have 71.4 gram uranium. So this gram and this gram can get cancelled, and your answer will be in kilogram, and then you can later on convert it to grams. So in the next slide it shows you how to do the calculation. Mass of kilogram of pitch blend times the mass of uranium over mass of pitch blend. So you start with 102. The ratio is 84.2 kilogram of pitch blend contains 71.4 kilogram uranium. Okay. And then you can convert kilograms into grams. 1 kilogram is 10 to the power 3 grams. 8.65 into 10 to the power 4 grams uranium. Okay. Dalton's atomic theory. So what did Dalton say? Dalton postulated all matter consists of atoms, tiny indivisible particles of an element that cannot be created or destroyed. Atoms of one element cannot be converted into atoms of another element. Atoms of an element are identical in mass and other properties and are different from the atoms of any other element. Compounds results from the chemical combination of a specific ratio of atoms of different elements. So that's what the Dalton's atomic theory in summary. Observations that establish the properties of cathode rays. Now I have posted a YouTube link for a video, so you guys can watch this video, and it tells us the experiment that discovered the cathode rays.
It was here in Cambridge that the first clear evidence for smaller objects inside the atom was found. Many of the great scientists of history have walked these streets, and one of the greatest was J.J. Thomson, who became the director of this, the old Cavendish laboratory. In 1896, Thomson had just got his hands on this new piece of kit. Now, it's essentially a particle accelerator. When this plate's heated, particles are emitted. They're accelerated by these electrodes. They pass through these two plates, across which you can apply voltage, and they hit the end of the bulb here on a screen which glows so you can see the beam. Now this is a modern version of Thomson's apparatus. Again, we've got the particle accelerator, and there's a screen in there so you can see the beam glow. What Thomson did was he varied the voltage across the plates, and he measured the amount of bending as the voltage changed. That allowed you to deduce the mass of the particles in the beams. Now, the lightest known particle in Thomson's day was the hydrogen atom. But Thomson found from these measurements that the particles in this beam are almost 2,000 times lighter than hydrogen atoms. Thomson had discovered the first subatomic particle, the electron.
The electron owes its practical utility to its smallness. If like apparently Shakespeare, then my use is great because I am so small.
The electron was the first discovery of a fundamental particle, and it is interesting to realise that more than 100 years later, the electron is still, to the best measurements we can do today, a fundamental letter of nature's alphabet.
We can use electrons as ways to probe materials and look at the structure in electron microscopes or in big machines like this accelerator behind me. Pretty much all of everything we do in the 21st century depends on understanding the properties of electrons.
Thomson had discovered that the atom is not the fundamental building block of matter. There are smaller objects inside. So atoms could no longer be thought of as hard, indivisible spheres. But how do the electrons fit inside the atom? Thomson suggested that the atom was something like this muffin, with the negatively charged electrons embedded in a positive body. It would be a student of Thomson's that proved him wrong.
Okay, so you have watched the video, that is the observation that established the properties of cathode rays. Okay, so what was the observation? Ray bends in magnetic field, and the conclusion consists of charged particles. And what is the charge of the particle? So there were two plates, positive and negative. Ray bends towards the positive plate, meaning the rays consist of negative particles. And ray is identical for any cathode, meaning particles found in all matter. And that is the observation that established the properties of cathode rays. And what is the cathode rays consist of? So they consist of electrons. So in the atom is not the smallest element or the smallest body, but now we have subatomic particles, that's the electrons. And then the Thomson thought the electrons are embedded in a positively charged body, and then it was proved that is not the case, right? Maybe we can do that in the next one. Okay, so Millikan's oil drop experiment for measuring an electron's charge. Once the electrons was found, and then later another scientist, Millikan, he did an oil drop experiment for measuring electrons' charge. So let's look at this video, how he conducted the experiment.
In 1909, Robert Millikan, working at the University of Chicago, succeeded in measuring the charge on the electron. He allowed a fine spray of oil to settle through a hole into a chamber where he could observe their fall. The top and bottom of the chamber consisted of electrically charged plates. He introduced a source of X-rays which can cause creation of charges when they strike matter. Charges produced by the X-rays attach to an oil droplet, producing one or more charges on the droplet. When there is no voltage applied, the fall of the droplets is determined by their mass and the viscosity of air through which they fall. When a voltage is applied, the droplets that have a negative charge will fall more slowly, stop falling, or even rise, depending on the number of charges on them. By adjusting the applied voltage and observing the droplets both with voltage off and voltage on, Millikan was able to determine that the charges on the droplets were all multiples of a smallest value, 1.6 times 10 to the minus 19th coulombs. He took this to be the charge on a single electron.
Okay, that was the Millikan's oil drop experiment for measuring the electron's charge. And then he found the charge of the electron is 1.602 into 10 to the negative 19. That also has helped to find the mass of an electron. And then the mass of the electron was found to be 9.09 into 10 to the negative 28 grams, meaning a very, very, very tiny mass, right? 10 to the negative 28. Okay. Okay, so I'm going to stop this part here. If I go too long, it would be difficult for me to upload onto the YouTube, so I'm going to stop.